Who doesn't like pretzels? Raise your hand if you don't like pretzels. Aha, see? Told you, everybody likes them. That's why Austin Peay State University recently got into the pretzel business. Yeah, it turns out we make pretzels, and we tell everybody that there are 454 grams of pretzels in the bags on the average. So maybe we could take that as our null hypothesis, that the actual mean is 454 grams. Okay? And we'll go along with that. We'll believe that because it's on the package, and we know that Austin Peay wouldn't lie to us, right? We have no reason to dispute that. It's status quo. Just go along with it. Now, I know that if that null hypothesis is really true, then if I went and I took a sample of, say, 25 bags then the sample mean, x bar, minus the actual mean over the sample standard deviation over the square root of the sample size would behave something like this, right? This is that t curve, that t distribution that we talked about in class, right? It's centered there at 0. So, what if, first of all, what if you did go and you took a sample and your sample mean was not 454 grams? What if it was 453 grams? Would you then dispute this? Would you say, hey, the average is actually lower than this? I don't know. Who really cares about 1 gram? Maybe 2 or 3 or 5 or 10 grams. What if it's how low does your sample mean actually have to be before you start second guessing whether or not you're being cheated? Okay, is it where do you draw the line? Is it 430 grams, 420 grams? And certainly if you get if you take a sample of 25 bags and you get 480 grams, you're not going to dispute that, right? So, in fact, you might even take your null hypothesis. Some books will write it like this, that it's greater than or equal to, like that. One thing about these null hypotheses is there's always some kind of equality in there. It might be an equal sign, or it might be a greater than or equal to symbol, or a less than or equal to symbol, but there's always some kind of equal sign in there, okay? All right. So again, I know that if the null hypothesis is actually true, if mu actually, if it's just plain old equal to this 454 grams, then if I go and I take a sample of size n, then this is, and if provided the sample size is large enough, or the values seem to be coming from a normal distribution, then this guy should be behaving like this, right? Okay, so maybe I'll take as my alternative hypothesis that the actual mean is strictly less than 454 grams. Okay, and so now this is what I do. I'll go and I'll take a sample to test. Take a simple random sample. Of size n equals 25. Okay, to test, and I'm just going to pull these numbers off the slide that's on the website there. These are the values from slide number 8, and I've already put them into my calculator here. I encourage you to pause the recording and do the same. Here they are. You can see them: 442, 456, 454, 438, 447, 449, 465, 449, 446, 447, 468, 454, 433, 463, 450, 446, 456, 435, 452, 444, 447, 447, 456, 456, and 450. There. Okay, 25 values. Okay. So there's my sample. And now what I'm going to do is I'm going to weigh all the bags, right? Going to average their masses, average their total masses. So I'll do one variable statistics there on list numero uno, and I get the sample mean is 450. Holy smokes, 450. 450 is indeed less than 454 grams. So already I'm sort of suspicious. We might be getting cheated. But is 450 something to really complain about? I mean, it's only 4 grams difference. Well, I don't know. The question here sort of runs around two ideas here: practical significance and statistical significance. Do we really care about 4 grams of pretzels? I don't know. It's really, nobody likes pretzels anyway. Oh, who am I kidding? We all love pretzels, right? The sample standard deviation in this case is 8.48 grams. I'll just round right there, 8.48. See that? And by the way, these numbers have units of grammage, okay? And, okay, good. So what I'm going to do now is I'm going to compute the value of this guy that I actually observe now. All right? And by the way, what mu do I use? This curve represents the behavior of this thing if H naught is true. Okay? So what I'm going to do then is I'm going to use this number for mu. That's why oftentimes you see an equal sign there. Okay, so this number, sometimes people denote it by mu naught because it's the mean. It's not the actual mean. They write mu naught. This is the little naught symbol. Okay, because it's not mu. That's right. It's not the actual mean. It's not the actual mean. You'll never know the actual mean. This is just the mean that is sort of prescribed by the null hypothesis there. Okay, see that? So it's a guess for the mean. The null hypothesis is that the actual mean is this guy. Okay, so I'll sneak that symbol there. So what I'm going to do now is I'm going to compute the value of this so-called test statistic, and if it's too far to the left of 0, then I'm going to go along with this. Okay, so our test statistic there is, and maybe I'll just abbreviate that like that. Test statistic is it's x bar minus mu naught over s over the square root of n, which is 450 grams minus mu naught 454 grams, dropping the units because I'm sloppy like that. Okay, divide by 8.48 over the square root of 25, right? Okay, I'm going to put that in my calculator. I get put that in parentheses, 450 minus 454 all over S was 8.48 over the square root of n. Oops, let me fix this thing here. There we go. Negative 2.358 or so. Okay, something like that. So, the question is, how strange is this? How strange is this number? How strange is that number? That is, how deviant is it? How far to the left of 0 is it underneath this t-curve? One way to measure that is something called the p-value. And we saw this with our spinning pennies activity. It was a little different back then, but it's the same idea. I'm going to measure the strangeness of this by computing the chance that I would see something this strange or stranger if, in fact, this test statistic should be behaving like this. That is, what's the chance that we'd see something this strange or stranger if the null hypothesis is really true? Okay? Well, here's how we can do that. I just want to get the area underneath that t-curve. This is that that same curve that we had before, but just to the left of negative 2.3585. Okay. This is our so-called p-value. P-value. We've got lots of p's, right? We've got p for proportion. We've got p hat, which is our sample proportion, right? P just by itself is the population proportion. We've got the Austin P. We've got the p-value. P-value is different. P-value is the chance you'd see something as strange or stranger given H naught, null hypothesis, is actually true. Okay, so I know how to get that area. In this case, okay, it's going to be the area underneath that t-curve, which I can get using that t-CDF function. Works a lot like the normal CDF function. T-CDF from negative 10 to the 99th, something way down there, up to negative 2.3585. And then I have to stipulate my degrees of freedom, which is going to be 24. Okay. This is, so here is your left endpoint, if there is one. Here's your right endpoint. And then this number that goes in here is your degrees of freedom, which for everything that we do in this class, it's just going to be the sample size minus 1. Okay. I'm going to do that in my calculator. Here it is. It's right here in the distribution menu, just like the normal CDF stuff. For a second, vars. Do it again for practice. Do it a couple more times so you get that muscle memory going there. Second distribution, right? And then it's there it is. Option number 6 in my calculator. And yours might be somewhere else. Don't pick TPDF. We don't need that. We need TCDF. C for cumulative. Okay. Okay. Negative 10 to the 99th, because we need to go way, way, way down there. We want to get the area from negative infinity up to negative 2.3585. Okay. And then put in our degrees of freedom, which is 25 minus 1. Okay. And phenomena, 0.0126. 0.0126. That's the chance that you'd see something as strange as what you saw if the true mean was really 454 grams. It's about 1%. Okay, there's a 1% chance that you'd see something that strange. So what do you think? Are you being cheated? Probably. Is it enough to write home about? Probably not. Okay, so I would say that this result is statistically significant. That is, there really probably is a difference there. You are probably being cheated, but it's the practical significance may not. Maybe we just don't care. Now, you're really going to love this. You're going to use our calculator to do all that mess. Okay, I have my data there in my calculator. It's in that first list. Remember that? Slaved over all this. Hey, by the way, if you want to remember these numbers, you can get them off the slides and the lecture notes for Chapter 9 slides on my website. This is on slide number 8 or so. The example about pretzels. Okay. Now, do this. Stat. Press the stat key. Remember the stat key. It's right there in the middle of the calculator. It's at the center of gravity of your calculator. Press it. And then arrow over to the tests menu. We're doing tests now. We're doing hypothesis test. You want to do a t-test. T-test Okay. Call it a t-test because it uses that t-distribution. I'm going to, hey, look at that. It gives me the option just to enter some statistics if that's all I have. But I actually have the data set, right? So I'm going to pick the data option. Make sure you highlight that with the enter key. Okay. Mu naught. It's the number that's not mu, which is 454, right? It's what the company claims that the mean is. I put my list in there, list 1. Freak. We've got one freak. Let's see, what kind of a test are we doing? The option you pick here is what's in the alternative hypothesis. Okay, use less than 454 grams. Makes a difference, right? Because you can, if you just look at this picture up here, if we'd gone the other way, then we would have gotten a really high p-value, right? It's the chance that we see something at this mark or larger, something like that, you know. All right. Anyway, makes a difference. You pick the right one. Got it. Calculate. Ready? 1, 2, 3, go. Okay. Look, there's our test statistic. Negative 2.358 something or other. It's about the same as what we got, maybe a little different due to some rounding error. It also reminds us the form of our alternative hypothesis, right? Our p-value, there it is, 0.0134. This is the most important number in your life, okay? The p-value. It's probably one of the most important things that you'll learn in this course. Everything is all about the p-value now, okay? And the idea is you reject the null hypothesis if the p-value is low. How low? Well, I don't know. It just depends on what's at stake. 5%, 1%, 2, 3% maybe, 0.5%, okay? I'd say that this is pretty low, okay? But we're just dealing with pretzels, so, you know, who cares? And so again, so that's the rule. You reject the hoe if the p is low, right? That's how it goes. I know it's lewd and crude, but you'll never forget it. If the p-value is low, reject the hoe.